Hello everyone, welcome back to class 12 Mathematics. Today we are stepping into the basic concepts of differential equations. This is the bedrock before solving anything in this chapter. Let's warm up with what you already know. Remember equations like x squared minus 3x plus 3 equals 0? That's purely algebraic, just x and constants. Or the trigonometric type, sin x plus cosine x equals 0. Or even the neat linear one, x plus y equals 7. All of these are static equations. They describe fixed relationships between variables, but nothing about how things change. Now imagine we shake things up. Suppose instead of just variables, we bring in their rates of change. Suddenly, equations gain life. For example, dy by dx plus y divided by x equals 0. Here, the slope of the function, the derivative, is involved. That's what makes it a differential equation. So here's the first big takeaway. Algebraic equations describe static positions, while differential equations describe dynamic journeys. Algebra tells you where you are. Differential equations tell you how you are moving. Now let's refine this idea. If a differential equation has derivatives only with respect to one independent variable, we call it an ordinary differential equation, or ODE. For example, d squared y by dx squared plus dy by dx equals 0. Here, everything is in terms of x. So this is an ODE. Think of real life. The cooling of tea depends only on time. The growth of money in a bank depends only on time. A spring oscillating back and forth depends only on displacement measured with respect to time. All of these are modeled by ordinary differential equations. But sometimes, life is trickier. Imagine temperature in a room depends both on time and space. That means two independent variables are involved. Such equations are called partial differential equations, or PDEs. Example, del squared z by del x squared plus del squared z by del y squared equals 0. But here's the good news. In class 12, we only deal with ODEs. PDEs come later when you study advanced physics, engineering, or even computer simulations. Right now, let's master the ordinary ones first. Before we move ahead, let's get comfortable with shorthand notations for derivatives. Writing dy by dx 100 times is tiring, so mathematicians invented symbols. First derivative, y dash, written as y prime equals dy by dx. Second derivative, y double dash, written as y double prime equals d squared y by dx squared. Third derivative, y triple dash, written as y triple prime equals d cubed y by dx cubed. But imagine going up to the 10th derivative. Writing 10 dashes would be ridiculous. That's why, for higher orders, we use power notation. Y with superscript in brackets n equals d to the power n y by dx to the power n. So the rule is, small orders use primes, higher orders use power notation. This way, equations look neat and easy to read, especially in physics where derivatives often go up to the fourth order. Next comes the idea of order. Order means the order of the highest derivative present in the equation. Let's test this with examples. Equation 1. dy by dx equals e raised to the power x. Highest derivative is first order, so order equals 1. Equation 2. d squared y by dx squared plus y equals 0. Highest derivative is second order, so order equals 2. Equation 3. d cubed y by dx cubed plus x squared into d squared y by dx squared equals 0. Highest derivative is third order, so order equals 3. So the trick is easy. Just look for the most advanced derivative. That's your order. No guessing, no confusion. Now let's meet the cousin of order, the degree. But degree is a little picky. It exists only if the equation is a polynomial in its derivatives. Here's an example. Bracket d squared y by dx squared close bracket squared plus y equals 0. The highest derivative is second order, raised to power 2. So order equals 2, degree equals 2. Another example, y double dash plus bracket y dash squared equals 0. The highest derivative is second order, raised to power 1. So order equals 2, degree equals 1. But if you see sine of y dash plus y equals 0, here the derivative y dash is sitting inside sine. That's not polynomial, so degree is undefined. So always check, is the equation polynomial in derivatives? If yes, find the highest power of the highest derivative. If no, degree does not exist. Let's try one together. Take the equation y double dash plus y dash cubed plus y equals 0. Step 1. The highest derivative is y double dash, that is d squared y by dx squared. That means the order is 2. Step 2. Check polynomial condition. Yes, y dash cubed is still polynomial and y double dash has power 1. Step 3. So the degree is 1. Final answer. Order equals 2. Degree equals 1. See how systematic it is? First check order, then degree. Time to tie everything together. We saw that algebraic equations involve only variables, while differential equations involve variables plus their derivatives. We defined ordinary differential equations as those with derivatives in only one independent variable, which is our focus in class 12. We learned derivative notations, primes for low orders, power notation for higher orders. We defined order as the highest derivative present and degree as the power of the highest derivative, but only if polynomial. And finally, we solved an example to cement these ideas. So the basics are clear. Order tells us how high we climbed in differentiation, and degree tells us how powerful the highest derivative is. In the next lesson, we'll explore general and particular solutions where differential equations turn into families of curves. That's where the fun really begins.